Okay, welcome to the CCHF Virtual Symposium and a special alumni edition. So we are delighted to be able to do the first of two meetings where we are going to be highlighting the research accomplishments of students and postdocs that have actually come through the CCHF and are now very successful in their own independent careers. And so today, the first of these meetings, part one, we have 5 speakers: Vincent Lindsay from NC State University, Julian West from Rice University, Peng Liu from University of Pittsburgh, Elizabeth Best from UC Irvine, and Carrie Engel from Scripps Research. And all of these 5 actually have had a major role in it. Has been role models in the centers. They were rising stars when they were in the center, and we're delighted to see how they've continued to develop from then on. So if I can have the next slide, please, Rio. So just people who may not be familiar with the CCHF, so this is a center now that's been going for close to 9 years. And it basically involves 23 faculty from 15 universities working together in the field of CH functionalization. And it covers many disciplines of chemistry. So it's actually a very exciting area for students to be exposed to various areas of chemistry. And what you're going to find is very exciting about our speakers is how they've evolved from their original areas into many other disciplines in chemistry. So because we were such a large center, one of the things we had to learn early on was virtual communication. Everyone's had to learn that a lot recently, but we had to learn this very early on. So next slide, please. So one way that we did it, of course, is the old-fashioned way. So once a year, we used to have this very exciting meeting where a lot of brainstorming. You'll actually see some of the faces of our speakers in some of the slides that are coming up. And the idea is to work as a team to think about how to maximize how we can impact together the field of CH functionalization. Next slide, please. And again, so you can see, you get certain stylistics. I'm not going to see if you can find the people in the meeting, but you see, we'll be hearing from Vincent first, and you can see Vincent was a back row player back then. So you can see him in the middle slide, right in the back row. And that wasn't quite the same with Julian, because coming from Eric Solons's group, he was more in the front row, as you can see with Julian on the right-hand side. And then the other people are hiding in some of these slides, and I'm not going to try to point them out to you at this stage. Okay, next slide, please. So because we had to learn how to communicate with each other, one big meeting, and actually twice a week, we used to do these really large-scale virtual meetings amongst the members of the center and the students, of course, as well. That in 2015, we thought we'd do something quite revolutionary, which was just to start to do a virtual symposia, like monster Zoom meetings, if you like. And of course, that is so passé in certain regards now, but this has been really exciting where we started in 2015. So this is the first round of the first 10 that we have. The next slide, please. Next slide, Rio, shows up to the 21st meeting. And I'm delighted to say now we're at the big number 22. Next slide, please. And as I said, we've had many of the sort of stars of the field of CH functionalization contributing to these meetings. And it's great today to be able to introduce the alumni from the CCHF who has played a critical role with us and are now doing extremely well in their own development. So next slide, please, Rio. Now, as I said, this is the first of 2 symposia. So in June the 15th, we will have a second round of 5 speakers from the center, now again in their own individual academic careers. So we hope you will join us for the second event as well. Next slide, please. One thing that we've started to do actually is to do sort of CCHF podcast. And we've just completed the first one, actually. And I want to highlight this because it's one of our speakers today who's the guinea pig who agreed to do this first event and hopefully enjoyed it as well. It's because often when we see scientists, we hear their story, but we don't always hear about what it's like for them as individuals in the field. And we're going to try to capture some of that going forward. And this was the first one. So I'd recommend, if you're interested, to listen to Julian and his thoughts about being a professor and how he became a professor and his future development. Next slide, please. We work very closely with the Division of Organic Chemistry with these symposia. They help to advertise our symposia, and we support technically their symposia as well. And I just want to mention that there's one coming up soon, May 19th. And there's two very interesting speakers, one industrial speaker, Carolyn Blakemore, and also Mary Watson from the University of Delaware. So I strongly recommend that you join these meetings as well. Next slide, please. So just to finish off with just a little bit of housekeeping, and Rio Furbian, who's the managing director of the center and is our technical guru. If I miss anything, please join in and say what needs to be done. So during the talks, all the microphones will be muted, but we do encourage questions, okay? And so if you're in Zoom, please go to the questions and answers at the bottom of the page and enter your questions. The talks, we have 5 talks. They're all going to be about 15 minutes or so. And so there may be time for 1 or 2 questions, but then we will encourage continuation of that discussion with the questions being answered in the question and answers of the Zoom, even after the next talk has started. So do that. We're always interested in pictures. We used to take pictures of people in lecture halls, all joining this event. Now we're encouraging people to come in with pictures with their pets. That's a much more appropriate thing to do this rather than joining as a big group, of course. Also, we're interested in getting feedback from you about how these meetings went. So there's a very easy way of doing that, which is put your iPhone next to this QR code, and that will take you immediately into a questionnaire that you can use. And of course, please follow us on Twitter, Facebook, Instagram, and LinkedIn. And Rio, do you want to say anything about Menti so that people can participate and show their responses to the talks as we progress?
Sure thing, Hugh. So if you have not noticed, but there are some reactions in the bottom of the screen, and if you would like to participate, and that's going to be our way to thank our speakers also, go to menti.com on your phone browser or your computer browser and use this code on the top here. They will pop up once in a while, and it's 5427-3104. So when you go there, you will see all these slides and you can react to it. It's kind of a fun, interactive way to do things.
5427-3104. I have it. Thank you, Rio. Okay, great. All right. So just to start the program, we thought we would go back a little bit and show you photographs of our 5 speakers when they were in the center. And most of them, their smiles were bigger. Maybe not Julian. Julian was a very serious student back then, or at least we caught him in a very serious mode here. And hopefully they're still smiling just as much in their independent career and still enjoying everything that they're doing. So anyway, so to start off the session, we're going to have Vincent Lindsay as our first speaker. So Vincent is originally from Montreal in Canada. He did his PhD with André Charette, and then went on to do a postdoc with Richmond Sarpong. And then in 2016, he began his independent career at NC State University. And he's done some really interesting work related to new methodology involving strain carbocycles driving these reactions. So we're very much looking forward to the talk, Enantioselective synthesis of modular cyclopropane equivalents and applications as highly strained building blocks. Welcome, Vincent.
All right, thanks you for the nice introduction. I appreciate, and I also appreciate the opportunity to be here today and talk to you about some of our chemistry that we've done at NC State University, specifically about the chemistry of cyclopropanones. But before I do that, since it's the alumni edition, I thought I had one slide to tell you about some of the work that I had done as a postdoctoral member in the Sarpong lab. And as a lab that is specialized in the synthesis of alkaloids, of course, some of the CH functionalization reaction that we're most interested in are intramolecular CH functionalization. So one of the methods that we developed involved the use of these sulfonyl triazole in an intramolecular CH insertion reaction catalyzed by rhodium. And then we can use a dependent amine here to close another ring to lead to N-heteral tricycles, as shown here. I also worked a little bit in total synthesis during my postdoc. We were interested in the synthesis of megellaninone. And as a key step, we thought we could do C3H functionalization of a pyridine using a method that was developed in the U lab at the time. And so we made this intermediate pretty rapidly. Like a lot of challenges in total synthesis, this does not work well, unfortunately, because of all the functionalities in this molecule. So that took us to a different path where we uncovered new rearrangement, namely an oxidation mine wall rearrangement sequence that led to a cyclopropane that we would use later on for vinyl cyclopropane, cyclopentene rearrangement. But the work that we do in my lab here at NC State is divided into two main programs. The first of which is the development of a novel bifunctional catalyst, more specifically these imidazolyl metal species that has a second functionality in the ligand that help the metal during the catalysis to achieve very high turnover numbers for sustainable cross-coupling reaction and also help to direct the regio control for CH functionalization reaction. But one of the projects that really took more expansion in the last few years in my lab is the chemistry of cyclopropanone, and more specifically, the use of sulfonylcyclopropanols as really well-behaved equivalent of cyclopropanones in order to achieve new synthetic disconnection, either keeping the cyclopropane ring intact by more classical disconnection, or through ring expansion methods to lead to 4 or 5-membered ring as well as fused heterocycles, or by ring opening reaction to lead to new deconstruction strategies. So this is what I want to tell you about today. And so the way we had this idea at the beginning is by looking at all the diverse chemistry that is already known with cyclobutanone, where you can do formal 4+1 or 4+2 cycloaddition to lead to ring enlarged compound like 5 or 6-membered ring, either using classical chemistry or more modern CC activation methods that were developed in the Murakami and Dong lab. Another example is shown here where you can do a classical semi-pinnacle rearrangement to lead to a spirocycle shown here, and that was used as a key step in the total synthesis of Friedericamycin A. And so we really wondered, since the cyclobutanone chemistry is so widely used in synthesis, why not cyclopropanones? Because when you look at the strain energies of cyclobutane and cyclopropane, these have about the same strain energy of around 27 or 28 kcal per mole. So naively, you would think that cyclopropanone and cyclobutanone could lead to similar types of disconnection. But in fact, when you add a ketone to these compounds, there's really a huge difference in terms of stability and strain energy. Where in the case of cyclobutanone, which are stable and a lot of them are commercially available, this is about 29 kcal per mole. But in the case of cyclopropanone, that goes up to 49 kcal per mole. And indeed, so this is highly unstable. You can make cyclopropanone by this method that was developed in the 60s by Thoreau and Hammond using ketene and diazomethane, although you have to distill this compound at -78 and use it right away. Otherwise, it will rapidly polymerize, which is the main decomposition pathway in this chemistry and really what we have to fight. Other decomposition pathways that are possible depending on the substitution pattern includes the light-induced decarbonylation reaction or Favorsky type ring opening to acyclic esters like this. And so because these are so unstable and difficult to handle, what people do when they really want to use cyclopropanone as a building block is they will use an adduct that will get transformed to cyclopropanone in situ to an alpha elimination reaction. And the most popular of these cyclopropanone precursors is this hemiketal shown here that was popularized by Wasserman in the 1960s. Although this does not work very well generally. First of all, the ethoxide here is not a very good leaving group, and we're forming something very high in energy. So you need some pretty harsh condition to trigger that equilibrium, and in presence of such an unstable compound, that leads to very low yield of desired rearranged product most of the time. Also, this same compound is known under basic condition to ring open to a metal homoenolate species, which is very practical in this field of metal homoenolate chemistry. But if you want to use it as an actual cyclopropanone equivalent, this is going to compete with your desired pathway. And a key paper for us came out in 2008 where Chen and his group reported that sulfonylcyclopropanol, shown here, was a very stable and crystalline compound, but most importantly was equilibrating to cyclopropanone under very mild condition, under weakly basic condition at room temperature. And so one of the only reported application at the time was this reaction in water at room temperature using an amine and a gold catalyst as well as an alkyne to form these compounds in decent yield. And so after working in my lab with different cyclopropanone precursor, we really saw that there was a lot of potential with these compounds and not much was being done with them. And we thought we could take advantage of this to invent new synthetic disconnection. And so the first thing we did is develop a general method to access unsubstituted Achiral version of these compounds. So starting from commercially available silyloxyketal shown here, we can cleave the silyl group on these compounds, and in one pot, simply add the sulfonate salt as well as formic acid and water. And that leads to these compounds in pretty good yield most of the time. This is all done in one pot and can be run on a gram scale. And interestingly, it doesn't need any purification, so only a simple workup gives the pure compound right away. And so we can access a wide range of these compounds and with different leaving groups, so either with an electron donating or electron withdrawing group at these positions, or we can have alkyl groups as well. And one of the reasons why we did so many of these is that we wanted to evaluate their propensity to equilibrate to cyclopropanone and see if we could control that equilibrium. And so in order to measure that, we look at the kinetic study of a pyrazole trapping reaction that we had developed, where in this case, the equilibration to cyclopropanone is the slow step, while the addition of pyrazole is very fast. And so if we follow this reaction by an MR, that should give us an idea of their relative propensity to equilibrate to cyclopropanone. And indeed, we saw that there was really a huge effect of the R group here to the equilibrium constant to cyclopropanone, where electron-rich aromatic sulfone leads to a lot slower reaction compared to electron-poor para-CF3 or para-nitro derivative, for example. So that's for the electronic effect. But there's also a steric effect where, for example, if you got a tributyl sulfone, that will equilibrate to cyclopropanone a lot faster than a methyl sulfone, simply because you have a more Pitzer strain release during that alpha elimination when you have a hindered group at this position. And so we can really access a wide range of equilibrium constant depending on the leaving group that we choose on the sulfonylcyclopropanol. And this is really important because, as I told you earlier, one of the main decomposition pathways that we're fighting in this chemistry is the polymerization of cyclopropanone. And so we want to minimize the concentration of cyclopropanone at all times in solution. So every time we want to develop a new reaction, we need to be able to adjust the equilibrium constant and match this constant to the constant of the desired reaction. So we need to be able to modify this equilibrium constant at will. Now, all of these compounds are precursors of Achiral unsubstituted cyclopropanone. And so we really wonder, can we access an enantioenriched version of these compounds? And by looking at the literature, we found that there's really no general route to an enantioenriched cyclopropanol, surprisingly. And so the best way that we found to do this was to use known methods from the literature to access enantioenriched sulfonylcyclopropanes, either starting from a methyl phenylsulfone or a diazolsulfone shown here, and develop an alpha-hydroxylation reaction to lead to enantioenriched sulfonylcyclopropanol. Now, hydroxylation of sulfone is really not a common disconnection in synthesis, and so we really had to develop our own method here and optimize this reaction. Where one of the challenges that we had is that these compounds are unstable to base. They will equilibrate to cyclopropanone under basic condition, but the hydroxylation of sulfone required base absolutely. And so we need to be able to run this reaction at -78 and having a powerful enough oxidant to react at -78, and then quench the reaction at -78 to freeze this compound in the protonated form. And so we found these specialized conditions, and we're able to access a wide range of aromatic derivative as well as aliphatic substituted derivative. A CF3 and more congested substrate are also possible, as well as a bicyclic derivative, which are interesting when you think about the Favorsky rearrangement. Well, these are typical Favorsky rearrangement intermediate that are kind of frozen in time as a sulfonylcyclopropanol. So this reaction has an unusual hydroxylation mechanism, and the way we discovered that is when we did the optimization, we really found out that we needed absolutely a BF3 type of Lewis acid, or at least a boron Lewis acid, for the reaction to work, and this needed to be added before the oxidant itself, otherwise the reaction wouldn't work well. And so the presumed mechanism is the following. So we first deprotonate the sulfonylcyclopropane. That reacts with the BF3 to form a lithium trifluoroborate that will then lose a fluoride ion to cleave one of the silyl group of the oxidant. These two species can then recombine, and after a 1-2 shift and protonation, we're able to access the cyclopropanol. And the way that we note that this is the effective mechanism is if you replace the oxidant by a bis-silyl pinnacle region instead, you can isolate the corresponding pinnacle boron region, showing that we really form a carbon-boron bond before forming the carbon-oxygen bond. And so we can run this whole sequence on gram scale efficiently. So this is how we make one of our substrates. So starting from phenylmethylsulfone, you can buy this epoxide in an enantiopure form, so it's relatively cheap. And you can do a sequential nucleophilic substitution reaction under these conditions to access the sulfonylcyclopropane in decent yield on gram scale. And by applying our hydroxylation condition, we can get 80% yield and more than 99% E for this cyclopropanone precursor. Now, in order to access more derivatives of these, we have now a more divergent approach starting from epichlorohydrin, which is really a great source of chirality. And so it's really cheap and it's an enantioenriched form as shown here. And so if you simply add a cuprate to this epoxide, that leads to an alcohol like this that can cyclize to form another epoxide that can be used for the same sequence I just showed you up there. And so if you want to modify the R group at this position, you just have to choose a different grignard in the first step here. And so now that we have access for the first time to an enantioenriched and modular cyclopropanone equivalent, it was time to develop a new synthetic disconnection using these compounds, either using more classical chemistry like grignard addition to lead to cyclopropanols, or Wittig to lead to alkylidenecyclobutanon, but also more modern reaction like CC activation, formol 3+1 cycloaddition, as well as oxidative ring openings. So I'm going to give you an overview of these methods that we developed so far. So last year, we were able to develop this grignard addition reaction that looks simple at first, but remember that every time that we develop a new reaction here, we have to control the equilibrium leading to cyclopropanone. And so this demanded quite a bit of optimization and was developed by Roger Mechani in my lab And so we have three different methods for this to access tertiary cyclopropanols. Either you can use an excess of Grignard where one equivalent is used as a base to equilibrate to cyclopropanone. If your Grignard is more expensive, you can also use methyl Grignard as a sacrificial base at -78. And for alkyl nucleophiles, it's better to use zincates, while the use of alkyl Grignard don't work really well. And so with that, we can access either electron-rich or electron-poor tertiary cyclopropanol, as shown here, as well as sterically hindered derivative work very well in this reaction. And most importantly, we can access chiral tertiary cyclopropanol, which are very difficult to access by other methods, namely the Kolinkovich cyclopropanation, for example. And recently, we're able to find that you can also have a pyridine derivative adding to the cyclopropanone in moderate yields. Another classical reaction you can think of doing is a Wittig reaction. Now, once again, this demanded quite a bit of optimization. I'll keep these conditions vague because this is still an unpublished result. But you can access Enantioenriched electron-poor alkylidene cyclopropane in Enantioenriched form through this approach. The problem with this reaction is the DR, where we cannot really control the stereochemistry of that double bond very well. And so in order to get around that, what you can do is add a nucleophile to this electron-poor alkene to lead to beta amino acid derivatives. For example, you can also use glycine or homoglycine nucleophile, and that leads to peptide or dipeptide type of products, as shown here. Another reaction we thought of doing here is inserting a nitrogen inside the three-membered ring, and that would lead to beta-lactam, especially these 4-chiral beta-lactams that are difficult to access otherwise. So organoazide did work a little bit in this reaction, but we found that a milder approach that would lead to a higher yield was to use hydroxylamine as a nitrine equivalent under these conditions right here. You form first the hemiaminal that can rearrange to a 1,2 shift under a Lewis acid condition. And so you can use either the free hydroxylamine, the O-benzyl hydroxylamine, or the HCl salt, depending on the commercial availability. All of these work well, and you just need to adjust the conditions a little bit. And so aliphatic hydroxylamine work well as aromatic ones. The yield goes up when you use a chiral substituted cyclopropanone equivalent, and you can get full regio control in terms of the 1,2 shift for these 4-chiral beta-lactams. And so if you use an enantioenriched substrate, you can run this reaction on gram scale and obtain full transfer of the stereochemical information to the corresponding beta-lactam here. Following this, we also wanted to insert a carbon in a three-membered ring, and that would lead to a cyclobutanone. So we first started by regular carbene equivalents like diazo compound, but these did not work so well in our hands. But what did work well is more classical chemistry using our own Grignard addition. So if you add a vinyl Grignard, that leads you to an allylic alcohol that you can use crude. Treat that with NBS to form the bromonium that will rearrange through a 1,2 shift. And after elimination, that leads to an alkylidenecyclobutanon in an enantioenriched form. And so that works well for different substituted derivatives, as well as substituted Grignard derivatives as well, as shown here. If you use an alkynyl Grignard instead, what you get after this sequence is a bromoalkene that you can use in a subsequent Suzuki cross-coupling reaction. This is relevant because, for example, here we had an ester which we could not use in our Grignard addition, obviously. And if you have a substituent at the 1 position of the Grignard, that leads after the sequence to an all-carbon quaternary center and very good enantioselectivity with dependent neopentylic bromide group here. And so the same allylic alcohol can also undergo other types of ring expansion. And so if you use our sequence I showed you earlier, what you get first is the alkylidenecyclobutanone. But if you add a Lewis acid to that, the succinimide that was liberated in the first step from the NBS can reattack to form a beta amino ketone as shown here. If you use HCl to protonate the double bond, that leads to a saturated cyclobutanone. MCPBA can also be used to epoxidize this alkene to trigger this rearrangement. And if you have 2 equivalent of MCPBA, that just continues on to make a 5-membered ring through a Baeyer-Villiger oxidation type reaction. Another type of ring expansion reaction that we wanted to explore was the CC activation of cyclopropanone. So there's a lot of chemistry done with CC activation of cyclobutanone, but this is actually the first CC activation of cyclopropanone, where we can insert an alkyne inside a 3-membered ring to form cyclopentenone. And so one of the great features of this reaction, it gives a full regio control with reverse Pauson-Can selectivity, where the large group of the alkyne is located at the 3 position, while in classical Pauson-Can chemistry, you'll get this large group at the 2 position here. And so all of these reactions I've shown you so far go by the formation of an anion at this position that will undergo alpha elimination to form cyclopropanone. But we really wonder what would happen if we form a radical at this position instead, to eventually lead to a ring open compound or a beta functionalized carboxylic acid derivative as shown here. And so this type of chemistry is pretty well known for cyclopropanols, leading to beta fluoroketones. And so if we do this reaction under the same condition with our cyclopropanone precursor, after hydrolysis of the species, what we get is a beta fluorocarboxylic acid. So in order to have a more divergent approach to lead to different carboxylic acid derivatives, what we thought of doing was to do a Pyrazole addition that we use for our kinetic studies, and using the same adduct in the fluorination reaction. That leads to an acyl pyrazole, which is already known to be a versatile electrophile in nucleophilic addition. And eventually that leads to a 3-carbon linchpin linking a nucleophile and a fluoride together to lead to acyclic beta fluorocarboxylic acid derivatives. And so a different substitution around the ring is possible in this reaction. And so we're working in racemic mode here because it's a radical ring opening. Of course, if we start from an electron-rich or enantioenriched cyclopropanone equivalent, we're going to end up with a racemic product. And so we have to work in racemic mode here. But nevertheless, it works with quite a bit of range of substitution to lead to a beta fluorocarboxylic acid derivatives that are difficult to access by conjugate addition, because typically this is a reversible reaction that is directed towards the alpha beta unsaturated compound. And so you can also use alcohols as nucleophile as well as hydride, and that leads to the corresponding alcohol. And so instead of fluorination, you can also do this with chlorination chemistry as well as iodination as well. And so this brings us to the end of my talk. And so I hope I've been able to convince you that these sulfonylcyclopropanol are really versatile synthetic intermediates. And I want to thank my group, of course, for their hard work on this. You've seen the names at the bottom of the slide. Eugen, Myungi, Roger, and Chris have all worked really hard to develop each of these reactions, as well as the initial study of learning how these compounds work. And so I'm really happy to be here at NC State. And thanks again for the invitation, and I'll be happy to answer any questions in the chat.
Okay, thanks very much, Vincent. Now let's see if I can get my Menti going. And how do we get the Menti going? That's better. Thank you. Please join me and thank Vincent for a great talk. Okay, Vincent, there's quite a few questions in the chat. I'm just going to ask one to you now. This is from John Tomlin, and he asks, for the 2011-2012 papers, did non-boron-based Lewis acids work but gave low yields, or did only boron Lewis acids provide any conversion to the cyclopropanol?
There was still some yield without the boron Lewis acid, but the yields were less than 10-15%. And so if you use more reactive oxaziridines, for example, that seemed to work a little bit, but these were kind of stoichiometric, pretty specialized region. And so it's possible to do a direct hydroxylation as well. It's just we couldn't really get a decent yield with that. And so, while we were optimizing, really if we come, all the other Lewis acid didn't work at all, and it's really only the boron Lewis acid that worked.
Okay, great. Well, please, everyone, please join me in Menti to thank Vincent for a great talk. And Vincent, there are some additional questions in the chat that hopefully you can follow up on.
Of course, thank you.
Thanks very much. Okay, so our next speaker is Julian West. So Julian also spent time at the University of British Columbia in Vancouver, and then he went to do his PhD with Eric Sorensen in the center at Princeton University. Was very active in the center, and actually went on to do a postdoc at Caltech with Professor Harry Gray and Brian Stoltz, another member of the center. And these days, he still has interest in CH functionalization, and he's got a lovely title for his talk, Radical Insights into CH Bonds. Welcome, Julian.
All right, thanks, Hugh. Let me just get this shared here. Okay, and let's see. Okay, so everyone can see my slides, all right?
Yes.
Okay, perfect. Well, thank you so much for the introduction, Hugh, and the opportunity to speak, to the old stomping grounds, a bit of a homecoming here. So,
Julian, so we can actually see your build order mini window on the corner there.
Okay, thank you. Okay, let me try this again. Okay, does it look good now?
Yep.
Yes.
Perfect. Yeah. New presentation here, but yeah, again, it's wonderful to get this chance to sort of reflect on, on the work that's been done and how this has sort of helped me in my own career here. So to start, I'll start with a little metaphor here, which is that, leading a research group, it's kind of like being a turtle on a fence post. And what I mean by this is that, there's really just no way that you get up on top of that fence post by yourself. So for me, a big part of getting up on top of that has been my involvement with the CCHF, starting with this really firm foundation of the community, just this great group of people. This is my mentors, Eric and Brian, but also informal mentors like Hugh, like Justin Dubois, Jin Guan Yu, the EOD directors, just a great network of friends and coworkers. Another step up to that top has been the inspiration that the CCHF has provided. We have so many diverse scientists that attack problems in CH functionalization from different angles. You're just, constantly learning new things and getting new ideas about, how to break these bonds and do that usefully. And finally, one thing that the center has really been good about is just providing these unparalleled opportunities. So, these are the annual meetings. These are things like these virtual symposia, but also really unique things like, like this new podcast series, like the VICHF trip to Japan, which for me was incredibly influential on my chemistry past and present. And, taking this all together, you can see when you map this all out, and really that last step to the top of that post, isn't so big anymore. So the CCHF has had a huge role in my development. And I'm actually going to start with some work in the CCHF where I thought a lot about molecules like this. So this is the acetinosyl or the CoA ester, thioester of oleic acid, which in animals like turtles is, how do we make this? And it's typically made in animals from actually the saturated counterpart in a twofold CH functionalization reaction, which is done by desaturase. So this is like a really interesting process. You're taking just this alkyl chain, you're cutting out 2 hydrogen atoms to make an alkene. So, how does this work? And, an early proposal from Breslow, sort of got the gross details of this. We need to remove these 2 adjacent CH bonds, but, I think we can all appreciate that this model is a little bit crude. And, as we've studied desaturase more, we've learned some more details, particularly that this monster doesn't eat both CH bonds at once, but in fact, The C9CH is the first course, and the C10 is the second course. So if we were to put this in a sort of chemical scheme, with some sort of generic alkane, starting from the alkane, we have our high valent iron oxo. This is able to perpetrate a CH cleavage event, break this strong 100 kcal per mole CH bond to get us to an alkyl radical and our singly reduced iron species. Now, what's really interesting here is that this same iron species then accepts that second hydrogen atom to get us to our alkane, or to our desired alkene. So it's this stepwise hydrogen atom transfer that goes through sequential reductions. Finally, to turn this over, in nature, we need to have some sort of terminal oxidant. For desaturates, this is typically O2, and this accepts both the electrons, and we remove both protons to regenerate our high valent iron oxo. But the real question here that got me scratching my head in Eric's group was, why do these two hydrogen atoms hop over? So if we actually think about the thermochemistry of a model alkane, so let's say cyclohexane, again, we know that this initial CH bond is very strong. This is 100 kcals per mole in cyclohexane. And this strength is part of the challenge of CH functionalization that the center really thinks about a lot. But what about this second hydrogen atom that's now adjacent to a radical center? What's the strength of that? It turns out that it is completely different, radically different, if you will. It's about a third the strength, 33 kcals per mole. So this bond is, for all intents and purposes, a completely different CH bond. And this divergence of bond strengths presented to me and Eric, this question of, could we address these two very different CH bonds with two different catalysts? And in this questioning, I was joined by a very talented then undergraduate at Princeton, David Huang, who's now a senior scientist at Amgen after completing his PhD with Tim Newhouse at Yale. And what we wondered is, could we use this polyoxymetallate on the left, tetrabutyl ammonium decatungstate, capable of breaking very strong CH bonds, well in the range of 100 kcals per mole, as has been demonstrated by Craig Hill, Davide Ravelli, Fagnoni, Yamase, Britton, the list goes on, a very well precedented photocatalyst. And could we combine this with another HAT catalyst, cobalaxine pyridine chloride here in the left, which has been used both in the radical polymerization literature at DuPont Central Research by researchers like Gridnev and Ittel, as well as in synthetic chemistry by some really, really groundbreaking studies from Jack Norton's group at Columbia. And importantly, what we saw here is, again, that this TBADT, this decatungstate, can break very strong bonds, whereas this cobalaxime has an effective abstraction ability up to about 50 kcals per mole, which should be able to remove a bond that is 33 kcals per mole in bond strength. Okay, so how we imagine this working is starting from this decatungstate in the bottom left, we photoexcite it, and then as we expect, this should be able to abstract that strong CH bond to make our alkyl radical. We then imagine that this alkyl radical could donate this weakened CH bond to the cobalaxime to make this cobalt hydride equivalent. And then we wondered if we could leverage the hydrogen evolution ability of cobalaxime to combine these two catalysts, close their respective catalytic cycles, and evolve dihydrogen as the sole byproduct. We're very happy to see that this worked, at least to some extent. So for cyclooctane, a very good dehydrogenation substrate, we were able to get 19% yield, which, while not a high number, is still corresponds to 48 cooperative turnover numbers, which is something for such a complicated system here. But what really left us scratching our heads is when we tried doing this with cyclohexane. So what we found is when we subjected cyclohexane to the same conditions, we did make some cyclohexene, but we made almost no cyclohexadiene nor benzene. And we were expecting that benzene would be the major product here because of that huge enthalpic driving force of getting that aromaticity. This is something that's seen in noble metal dehydrogenations. Why not in ours? So the answer actually falls out of the bond strengths again. So we know 100 kcals per mole, 33 kcals per mole, getting from cyclohexane to cyclohexene. But what about when we start from cyclohexene? So as we're all taught in sophomore organic, that first allylic CH bond is weak because we make this stabilized allylic radical. So we can think about this sort of resonance, being delocalized across this 3-atom system. And because enthalpy, it's just a state function, a difference in the energy of the starting material and the product, this stabilization of the starting material actually serves to strengthen the homoallylic CH bond and strengthens it to such an extent that actually there's no longer a driving force for a cobaloxime to do the second abstraction. So the reaction stalls because again, that cobaloxime has an effective bond strength of about 50. Here we're at 49, essentially thermoneutral. The reaction just stops in its tracks. So some really interesting CH functionalization chemistry in my mentored career. Then my independent career, we've sort of thought about flipping this idea on its head. Can we actually use 2 different catalysts to start making CH bonds, which might be heretical to this audience, but it's a pretty interesting problem. So here I was really fortunate to work with an outstanding postdoctoral researcher in my group, Dr. Venkatesh Katamuri, shown here on the right, who's recently accepted a position at Arcus and will be starting there next month. And Venkatesh and I were thinking a lot about using this iron acax species, which work from Holland has shown has an effective bond strength of about 16 kcals per mole, so incredibly weak. And then for our second hydrogen atom transfer, using venerable thiophenol, which has been used by many groups, Dennis Curran, Brian Roberts did some really foundational work on sort of polarity reversal catalysis. And yeah, so we wondered, could we actually use these 2 catalysts to start doing hydrogenation? So, we're not the first ones to think about using hydrogen atom transfer to achieve hydrogenation. In fact, some really foundational recent work from the Shenby and Herzon groups has revealed that this metal catalyzed hydrogen atom transfer is a very versatile method for hydrogenating olefins. So, using some metal, so in Shenby's case, this is a manganese beta diketonate in the presence of a silicon, a silane hydride donor and a oxidant, they're able to get very, very high yielding hydrogenations with thermodynamic stereo control, as opposed to the sort of kinetic cis orientation that you need to get in noble metals or palladium type hydrogenations. And then similarly, Herzon and coworkers at Yale have found that cobalt is able to do this kind of chemistry as well. Importantly, this kind of reaction also tolerates functional groups that are not tolerated under noble metal reactions, such as vinyl halides. You're able to keep that CX bond intact. So a really powerful method. And how these methods are thought to work is through a Mukayama type metal catalyzed hydrogen atom transfer cycle. So again, starting from this metal hydride on the left side here, we can think about this, again, less than 20 kcals per mole bond being delivered to that olefin to make that about 33 kcal per mole CH bond. So there's a driving force for this hydrogen atom transfer, which then gets us to this metal 2 state. But this metal 2 state is unable to accept a hydride from the silane. So we actually need a stoichiometric oxidant here, in addition to that reductant, to return that metal in the 2+ state to the metal 3 state, which can then again accept that hydrogen atom. But so this is how the first hydrogen atom transfer here works. So we need that oxidant again to regenerate that M3. So how this is thought to actually get to the hydrogenated product is through 2 turns of the catalytic cycle. So here again, we're using this very weak MH bond to form that very strong, about 100 kcal per mole CH bond. So this MH is way overkill for this second step. we don't need something nearly that weak to achieve this hydrogenation. So, this got us to this question, could we introduce a second catalyst with a much stronger XH bond? And in so doing, could we think about eliminating the oxidant and perhaps, only getting one of our hydrogen atoms from the silane and our other one maybe from a protic solvent? So how we thought about this looking in a catalytic cycle is, again, starting from this iron hydride, we donate that to our alkane to make our iron 2 and a alkyl radical. This alkyl radical can then accept the CH bond from our silane to make a from our thiol to make a thiol radical. And we wondered, could this oxidizing thiol radical then serve as a in situ generated oxidant to return our iron to the 3+ state, make a thiolate, and this thiolate can then be protonated to regenerate our thiol. So again, one of our hydrogen atoms is coming from the silane and one is from the solvent. So, so we were very happy to find that with just 10% of both catalysts, iron ACAC and thiophenol, very cheap, very abundant catalysts, we were able to hydrogenate a variety of alkanes with 2 equivalents of phenylsilane. So unactivated alkanes, we were able to get that same thermodynamic stereo control as Shenvi and Herzon, as well as that same tolerance of vinyl halides. What's really interesting is, we were wondering about the provenance of these 2 hydrogen atoms. So we did some labeling studies. So using, again, the same system, what we found is if we use deuterosilane, we got exclusive labeling at the position that the iron donates the hydrogen atom to. By contrast, if we use proteosilane but deuterosolvent, we got exclusive labeling at the position that we attribute the thiol hat to. So again, this very much supports this kind of mechanism. And finally, we had a very interesting sort of parallel to our work with the dehydrogenation, which is this sort of enthalpic gating effect. So here again, this hydrogenation here to make this, this butyl benzene works very well. And we can think about this because this hydrogen atom transfer from thiophenol, 84 kcals per mole, to the alkyl radical to make this 98 kcal per mole bond, there's a huge enthalpic driving force here, minus 14 kcals per mole. So this goes in about 93% yield. It works really well, great driving force for this thiol hat. By contrast, if we use this diphenyl ethylene intermediate here, again, we have 84 kcals per mole from the thiol, but here it turns out that actually this this tertiary center that's bisbenzylic is weaker than the thiol. So when we tried this reaction, so again, this is endothermic, and it actually doesn't work under our conditions. So we see that there's this sort of cutoff based on bond strength for the reactivity of our system, which we thought was a really sort of interesting outcome of the mechanism. So future directions, we're really interested in this labeling. Again, this idea of controlling labeling by reagents and catalysts. We're interested in introducing some enantioselectivity, which we do have some promising results on that aren't quite ready to be shared yet, but we're working hard on that. And, again, just now I move into some acknowledgements, a few photos I dug up of some really great times in the CCHF. I'll call out particularly this top right photo. So you can see me there with the current or the then EOD director, Dr. Lloyd Majunja, who was just a fantastic individual. We were at SACNIS doing some outreach for CCIs, just an outstanding opportunity. Some pictures from the Japan trip here as well, some bowling. Here again, some acknowledgements for the dehydrogenation. Really amazing group of people in Eric's lab. Supported by several fellowships, CCHF, some other grants there. And finally, for this last portion, really in debt to my current research group, just an amazing group of people. You can see Venkatesh there in the top right. We've been lucky to have funding from CPRIT in Texas, as well as Rice University. And with that, I'd be really happy to take any questions in the chat. And, again, thank you so much for this opportunity to share my journey from breaking CH bonds to making them.
Very nice, Julian. I was very impressed with you when you were in the center, because you were always thinking about methodology outside of the normal box, including what we were doing in the center. It's really impressive. And I think you're showing that same attitude with your own independent career. So congratulations. We got one question to ask you right now. If anyone's got other questions, please put them into the question and answers. But the question I want to ask you is from Jiang Yang. The cobalt derivative might be too weak to extract a hydrogen atom from cyclohexenyl radical to give the cyclohexadiene, but the molybdenum catalyst is strong enough, around 100 kilocal per mole. Why
Right.
does the molybdenum derivative would not abstract the hydrogen to generate cyclohexadiene?
Right. No, that's a really good question. So yeah, like we saw with the Herzon and Shenvi chemistry, why can't we use the same catalyst for both steps in the dehydrogenation? And you can, to an extent. The issue here comes in two forms. One is that we're relying on that cobalt hydride equivalent to turn over both catalysts. So unless we have that sort of hydrogen evolution sort of cycle and hydrogen atom transfer cycle present, we're not going to be able to remove that hydrogen atom from the decatungst state to get us back to the ground state. You may be able to with a terminal oxidant if you included that, but you won't be able to get this acceptorless action. And the other challenge that the dehydrogenation has that the Herzon and Shenvi hydrogenation doesn't have is that this decatungst state is a photocatalyst with a relatively long lifetime for a photocatalyst, but it's not infinite. So the instantaneous concentration of this photoexcited decatungst state is incredibly small. So the chance of two photoexcited catalysts finding that same molecule before it goes and does something else bad, like coupling, is, you're just fighting a very difficult kinetics game there. So what we found is by having this ground state cobalt complex, which is in a higher concentration, we're able to shut down coupling and get really selective dehydrogenation. But yeah, that's a great question.
Okay, Julian, there's additional questions in the question and answers. Hopefully you can join that and continue the discussion. But once again, thank you for a brilliant talk. Well done.
Thank you so much.
Okay, so our next speaker is Peng Liu. So Peng Liu did his BS at Peking University, and then we've got a third Canadian connection. So he did his master's first at Guelph, and then he went to do a PhD at UCLA with Ken Houck, and then during that time, he was incredibly collaborative, not just within the center, but actually beyond the center as well, following actually the great example that the Professor Houck shows in terms of broad-based collaboration. And that type of activity has continued in his own independent career, where he's made a lot of connections with various experimentalists and has been really impactful in his independent research career since 2014. And we're looking forward to hearing various aspects of that work. The title is Computational Approaches for Mechanistically Guided Catalyst Discovery. Looking forward to your talk, Ben.
Yeah, thank you, Hugh, for the introduction. And I just want to start by thanking the CCHF to really provide this a wonderful opportunity for me to share our research. Not only that, CCHF has made the wonderful connections to for me when I was a PhD student and postdoc in Ken Houck's group. to this wonderful group of people. But really, I got a lot of inspiration from those discussions. I still remember these 2-hour weekly meetings where I learned everything about organic chemistry. And I was fortunate enough to get the chance to collaborate with various research groups back in the center. And of course, I had also fortunate to get to know a lot of the talented PhD and postdoc students in the center who now have started their own independent careers. And my interaction with the center didn't stop after I leave UCLA. And in fact, I started my own collaboration with Risman Sarpong's group, who actually I first met at one of those CCHF center meetings, and also John Montgomery's group. And of course, we have this very productive collaboration with Carrie Ingo with 12 collaborative papers so far and growing. And we also just started another collaboration with the Hill group on another collaborative projects. And I think everyone can probably have a long list of the achievements or impacts. CCHF have really transformed the whole scientific community. But to me, what's the most inspirational is that CCHF really taught me that there is a strong desire that organic chemists should change the way that we work, right? So what I learned when I was in the center is, people really want to collaborate, and when there is a possibility that we may change the way that we work in whatever you develop the chemical reactions. So what we've been thinking is, if you think about the typical catalyst development approach, and you can probably summarize that into this so-called waterfall model, which is particularly a linear approach, have this very logical steps. But of course, the shortcoming of this is, the center of this is based on a lot of a trial and error experiment. And, there is very little mechanistic insight, when you actually optimizing your catalyst. And we were wondering, is there a way that, we can work together between computational and experimental chemists, and we can transform the way that we develop catalytic reactions. And we thought, if we have this opportunity to have this real-time collaboration, and maybe we can propose this entirely different way that we discover new catalytic transformation. Let's say if you already have some preliminary insights about the mechanism of the reaction, then we can calculate whether a catalyst is reactive or not, or selective or not, and we can make this predictions to experimental system in terms of how to improve a existing catalyst system, and the experiment can then be used to validate the computational predictions, and then we use this sort of iterative approach that eventually leads to a catalyst discovery. So this approach sounds promising, but then we've been thinking, how can we make this work? At least computationally, we need to address two fundamental questions. Again, we think we have some reasonable ways to get energies and geometries from our computational data, right? But that doesn't tell you how to basically modify your catalyst system. So we really need to get this so-called on-the-fly understanding from these close interactions. In those processes, we have to make sure we want to minimize the human bias when we interpret the computational data. And also, eventually, we want to make our computational mechanistic studies much shorter than the typical time that we will need to investigate those reactions. Hopefully, by shortening the time for a computational mechanistic study from months to days, or maybe in the future to hours, to get some useful insight that can be used to guide the experimental development. So, and of course, if you can achieve that, you can list a number of benefits, right? So the key of this is we hope this can accelerate the catalyst discovery by providing the rational insights into catalyst design. And also we think that this approach can also save the resource, both in terms of reducing the number of experimental screening and also reducing the number of catalysts that we have to calculate or screen computationally. So our philosophy in terms of getting to those on-the-fly understanding is, as I mentioned, we need a robust and unbiased computational approach, but the end result should be human interpretable. because we still want to get immediate insight that can be used for the rational catalyst prediction. And we think we want to deal with a relatively small number of catalyst structures computationally, which means that we want to do high-level quantum mechanical calculations, but we want to provide high-quality data that will be reliable even with the smaller number of catalysts that we studied. So with those in mind, we first explored the use of energy decomposition analysis to study transition metal catalysis. So the idea is, we can use a similar approach that's related to the distortion interaction model proposed by my previous advisor, Ken Hauk. So we can separate the activation energy into three different energy terms. We can first calculate the distortion energy of the catalyst and the substrate, and then we separated the interaction energy between the catalyst and the substrate into two different types of interactions. So we can first calculate the so-called through space interactions, which basically is the non-bonding interaction between the ligand and the substrate itself in the absence of the metal center. And then the rest of the interaction is the through bond interactions. So the benefit of doing this is then, we can have a very careful look at the non-covalent interactions between the ligand and the substrate by using this second generation ALMO EDA approach in QChem5. So using this EDA approach, we can separate this through space interaction into several energetic terms which are chemically meaningful. So these include the Pauli repulsions or closed-out repulsions, electrostatic attraction or repulsions, polarization, charge transfer, and also London dispersion interaction and the solvation energy. So the bottom line is, if we are given any two transition state, and if we do this energy decomposition analysis, and we can immediately tell which one of those many components is the dominant factor that affects the relative energy of those two transition states, and immediately we'll know some mechanistic insights that will tell us about the different catalyst reactivity or selectivity. So we first applied this approach to a copper hydride catalyst hydroamination reactions in collaboration with Buckwood. So the Buckwood group has established experimentally that the use of this diterbutyl paramethoxy substituted DTBM cycphos ligand leads to much more enhanced reactivity experimentally. And this actually agree with our calculated activation barrier for this hydrocupuration step. But of course, the calculation, this type of calculation itself does not tell you why this ligand works better. By using our EDA approach, we separated the activation energy into those energetic terms I mentioned earlier, and it was found out that the dominant factor that really distinguishes these two catalysts is the dispersion interaction between the ligand and the substrate in this particular transition state. So this type of insight is useful because we can use this to guide us into this stepwise ligand optimization approach. So in collaboration with the Buckwood group, as you can see, after we get the insight about why DTBM cycphos works a little bit better than cycphos, and then we proposed several different iterations, including introducing fluorine substitution here, where we found they can promote reactivity by more favorable through space electrostatic interactions, and then we can further increase the dispersion and also catalyze the stability in the stepwise approach, and eventually we can get to this experimentally much more reactive ligand system for this hydrocupuration reactions. So we were pretty excited about this. We actually applied this to some other catalytic transformations. Using this similar EDA approach, we have studied there's two different types of asymmetric transformations where dispersion interaction promotes the reactivity and the enantioselectivity. So this is useful because if you think about the typical quadrant diagram type of a process for asymmetric transformations, the typical catalyst usually works by disfavoring the undesired pathway due to steric repulsion, right? But let's say if you have a favorable dispersion interaction in the more favorable pathway, so in this case, you're not only promoting the enantioselectivity, by increasing the energy difference between the more favorable and the less favorable transition states, but you're promoting the reactivity, right? Because the more favorable pathway will be promoted by the attractive stabilizing dispersion interactions. So in fact, in these two different reaction systems in collaboration with Dong and Harwick, we found that this dispersion not only increased the enantioselectivity, but also allowed this rhodium callus to cleave the carbon-carbon bond at room temperature. And with Harwick, we found by using a large main group substitution on this ligand scaffolds, we can increase not only the enantioselectivity, but also the reactivity of this copper callus in hydroboration reactions. And of course, we can also use the EDA to study other type of systems where the callus reactivity is not controlled by dispersion. So in a collaboration with the Yinggo group, we demonstrated that the ligand effects for this modified DPP-BZ type of a ligand in this copper catalyzed alkene hydroboration reactions is essentially controlled by the through space electrostatic interactions if we have a more electron deficient R group here, so that will actually promote the interaction to give you a more reactive catalyst. And we can also use EDA to look at through bond interactions. So in the collaboration with the Hall group, so we look at the radial divergent alkene nucleopolidations. This is a sort of a classical question about radial selectivity, about Markov-Nikov versus anti-Markov-Nikov reaction pathways. So using the EDA, we were able to demonstrate how, depending on what palladium callus or nucleophile was used, whether the dominant factor leading to a particular radial selectivity is controlled by electrostatic interactions, orbital interactions, or the steric repulsions. So these all sounds very promising, right? So it seems like, again, if we're given any two transition states, we will have this robust way to explain what the dominant factor is to give us understanding. But while we are very excited to apply this to more systems, we also realize a number of limitations of this mechanistically guided approach. So the reality is, especially in the context of a transition metal catalysis, there are a large number of systems that are still very challenging for us to study. So, I have this long list, right? So of things that we want to sort of avoid as a computational chemist because they're really challenging. And they're especially challenging if you want to make a very quantitative and accurate predictions. And we have been wondering in the past several years, what are the potential solutions to these key problems? We have been making some progress in the area in terms of especially studying the flexible system and complicated reaction pathways involving multi-components. And but today, I just want to tell you one of the projects where we use metadynamics simulations to study reaction systems where explicit solvation effects are important. So we started with a very simple reaction system, actually without a transition metal catalyst, but this is a classical problem about the solvent effects on reaction mechanisms. So in this particular glycosylation reaction, and of course, this may give you either a sterol retention or sterol inversion product. And the way we teach sophomore organic chemists is that, if you get a complete inversion, so that suggests that this is SN2 reaction pathway, but if the reaction occurs through this SN1 mechanism, so you will get a mixture of both stereoisomers, right? But the reality is not that simple, so it's not either SN2 or SN1. The real system is more complex. So in fact, the most of the reaction probably occurs through a mechanism that's between SN2 and SN1. For example, that might involve a contact iron pair where the leaving group is not completely dissociated before this nucleophile attack this oxocarbenium contact iron pair. So this phenomenon was described as a continuum of reaction mechanism, but of course, this poses a significant challenge for computational investigations, especially considering solvent would have a significant impact on the reaction mechanisms. So how do we address this? We thought we can potentially use this ab initio molecular dynamics simulations in the presence of this explicit solvent molecules. So the benefit of doing those MD simulations is, we can get a lot of data. And from this data, we can get some quantitative metrics or indicators that tells us where exactly is our reaction mechanism in this SN1, SN2 continuum. So the indicators include, the surface of the energy surface, and also the synchronicity of the transition state structures and the timing of a bond cleavage and formation. So the reason we want to get this quantitative descriptors is because those quantitative indicators can tell us the mechanistic information in a very robust way, but also human interpretable that really fits very well into our philosophy in the new approaches of studying reaction mechanisms. So we use this metadynamic simulation to model this particular transformation. As I said, we can get the free energy surface starting from the activated starting material through a transition state. Apparently, this is a one-step reaction if you follow the minimum energy reaction path. And we can also locate the transition state of this process, and we can get the bond distance. Apparently, this is very similar to a loose SN2 type of a transformation. And from the MD simulations, we can also get the timing in terms of the time, the average time between the C leaving group cleavage and the C nucleophile bond formation. In this case, we have a very short time gap between these two events. We call this type of mechanistic process dynamically conserved. And of course, we can repeat the same simulations by using a different solvent. In this case, if we use this MTBE ether solvent for the same starting materials, we found the energy surface actually become completely different. In this case, SN1 type of mechanism is favored. We have this stable intermediate in the free energy surface. And the transition state geometry also becomes more asynchronous. One of the CO bond is very long, the other bond is much shorter, and the timing between the C leaving group cleavage and the C nucleophile formation is much longer. So every indicator suggests this particular mechanism is more SN1-like. So what that means is we do have those quantitative metrics that tells us information about the energy, the geometry, and the timing of those processes. And we can routinely apply this to different reactions involving different solvent, different acceptor. And by doing so, we can get this quantitative descriptors that tells us what type of reaction, not only what type of mechanism, but where exactly is your mechanism located with this SN1 and SN2 reaction continuum. So with that, I just want to conclude my talk, but I hope, I convince you that studying mechanism is fun, it's important, it's useful potentially can be used for catalyst design, but of course there are a lot of practical issues that remain to be addressed. That's basically why, my entire group is fully motivated to study this. So this is apparently a picture before COVID, and so now we are still in the remote mode. So this is my current group. I would really want to thank all of them, and again, so thank and CCHF for this wonderful opportunity to share our scientific findings with you guys.
Are you there, Hugh?
Yes, I was saying wonderful things about you, Peng, and that everyone missed. Great talk. It's you're covering a really interesting range of chemistry and having a really big impact. So congratulations. So because of time, I think we will go straight on to the next talk. So if there's any questions, please put them in the questions and answers, and Peng will be able to respond to them at that time. So our next speaker is Elizabeth Bess, and Elizabeth came to the center from Professor Matt Sigmund's group, and really bringing in sort of new techniques in terms of thinking about catalysis, in terms of bringing in new quantitative tools to analyze reactions. And again, she was very much at the sort of forefront of going further than where people had been before. And if I remember rightly, I think you spent some time at a pharmaceutical company as part of that sort of collaborative thinking, not just with academics, but also in an industrial setting as well, and made a big impact in that. And so as she was already going beyond the normal areas that most people would be thinking, it's not too surprising in her independent career that she's gone even further. And so her program now is a really interesting mix. We're thinking about fusing chemistry and microbiology together to understand chemical mechanisms by which the microbiome impacts human health and disease. And so you've got a lovely title. We're looking forward to hearing your talk, Finding a Catalyst of Gut Reactions. Welcome.
Thank you, Hugh. Let me share my slides here. Okay. Thank you for the opportunity to present here. It's such an honor to be back with this group, and my time as part of the CCHF now 6 or 7 years ago was really formative and actually helping guide my career to microbiology, and I'll tell a little bit of that story. So I guess the first thing to tell you is that you're not in the wrong spot. We are going to be talking about a little bit of CH functionalization, also the gut microbiome, and I'll tell you how my time at the CCHF kind of informed this transition. And it really comes down to, I think, this the idea that the CCHF is, I think, really promoting the beauty and joy in both collaboration, but also like cross-disciplinary discovery. And I think that can sometimes be daunting. And one of the things that was of such value to me in my time with this group was that it helped to break down some of those barriers of sort of diving into reactions or areas of science that you have no familiarity with, and then it's okay. And so that was something that was super valuable to me as my career went towards microbiology, and there were also specific interactions within the CCHF that kind of guided that. And I just wanted to highlight first here some of the folks that I had the pleasure of directly working with in the CCHF. And two publications that came out of those collaborations. One was a collaboration with the Dubois and Sigmund labs, where we were examining how we could use math to be able to pull out underlying features of molecules that we could use to predict selectivity of CH amination. With a collaboration at the Davies and Sigmund labs, we used a similar approach again to try to find what are these underlying trends, features of molecules that can help us understand patterns in reactivity. And with both of these collaborations, it exposed me to new ways of thinking, new kinds of metals that I hadn't worked with before, and was a real pleasure. I also had the great opportunity to go, as Hugh mentioned, to Novartis in Basel through the CCHF. This was something that was facilitated through the CCHF, through Larry Hammond, and also worked with Stephen Lutz at Novartis Bioreactions Group, Vlada Urlacher at the University of Dusseldorf. And here we were thinking about how we could take what we were learning about developing models in CH functionalization settings, as well as in other settings, and apply them to better understand reactions that enzymes are performing. And it was through this work in Basel that I first got to touch and work with bacteria, which was such a joy for me, and enjoyed it so much that my postdoc became that. And I think that those opportunities in sort of growing up in science around these ideas of celebrating both collaboration and interdisciplinarity really helped to facilitate and smooth that transition. And the rest of my talk, I'll tell you about some of the chemistry that happens inside of you in the collection of bacteria that live in your GI tract called the gut microbiota. These are trillions of bacteria that live inside of you. And every person's gut microbiota is different. It's as unique as a fingerprint. There are similarities, but also substantial differences across people. And this variability is important because it has functional implications. So in 3 areas of many where the gut microbiota composition impacts health is energy harvest, drug efficacy, and disease risk. So if 2 people eat the same meal, they have 2 different microbiomes, each one of them can extract different amounts of energy from the same meal. Depending on which bacteria are in your gut, it also impacts the efficacy of drugs that we use to treat disease. So there are some bacteria that are able to metabolize drugs, making them no longer active, and in some cases, even making these drugs toxic. And the microbiome is emerging as playing an important role in this equation. Added to, of course, the role that human enzymes play also in modulating drug efficacy. The composition of the gut microbiome is also important in modifying disease risk. So there is an accumulating body of evidence that indicates that which bacteria are in your gut can predispose a person to disease or even protect them from disease. So in my lab at UC Irvine, we're really interested in understanding these processes at a mechanistic level. We want to understand how are bacteria interacting with their human host and what is the communication that's happening between the bacteria and its host. And we think that something that is key to this is molecules, the molecules that are trafficking in this space. So I introduced that the microbiota is the trillions of bacteria in your gut. The microbiome is the sphere in which those bacteria operate. So this includes molecules, proteins, metals that are circulating within the gut microbiome that are impacting the behavior of those bacteria. Also, these bacteria are doing many different kinds of chemical reactions. And there are huge questions that remain open in the field about which bacteria are doing what kind of chemistry. In many cases, we don't know what the substrates of bacterial chemistry are, what the products are, what enzymes are involved. And so there is great opportunity in this field to really dive into the chemistry that bacteria are doing inside of us that I think are an important aspect of how the microbiome is impacting host health. So what I'd like to do today is to describe a approach to identify the catalysts that are within the human gut that are doing chemistry on molecules that are abundant within the gut, and how that can be leveraged to help us understand and maybe even engineer this space. And the case study that we'll dive into has to do with these 2 molecules that if you have eaten basically anything that has grown out of the ground, you have these molecules inside of you right now. These are pinoresinol and luriceresinol. These are molecules that are fairly abundant in the diet. And when these molecules, which are part of a class of molecules called lignans, when they reach your GI tract, come into contact with bacteria there, they get chemically metabolized to a downstream product called enterolactone. And enterolactone is a phytoestrogen that can interact with estrogen receptors. And through that interaction, there are several studies that show that when there are increasing levels of enterolactone within a human, there is decreased risk for breast cancer incidence. When rodent models of breast cancer are dosed with enterolactone, there's also a substantial decrease in tumor burden. What I became interested in is how is this happening? What are the bacteria that are responsible? What are the genes and the enzymes that are responsible? If we know these kinds of things, we may be able to ask questions about if a person may be likely to benefit from eating a lignin-rich diet. We could use this information as predictive biomarkers. Also, if we understand how bacteria are doing these kinds of chemistry, it opens up opportunities for engineering the gut microbiota to promote beneficial chemistry. So what is the actual chemistry that's happening here? First off, when you eat pinoresinol, it's particularly abundant in seeds and grains. This molecule, when it reaches your gut, will interact with a bacterium called Egerthalolenta. About 2/3 of us have Egerthalolenta in our guts, and this organism will first reduce the oxygen-carbon bond at the benzoic position of pinoresinol and lauriceresinol to form SACO. SACO then gets handed off to another bacterium in the gut that also most of us have called Blaudia producta, and this organism demethylates SACO to DM-SACO. The next step in this pathway is a third bacterium that dehydroxylates DM-SACO at the 4 position of the catechol. And this product is handed off to the last bacterium in the process, Lactonifactor longoviformis. And this organism does oxidative cyclization to form enterolactone. These last 2 metabolites in this pathway are the ones that are considered bioactive metabolites. They enter the circulatory system where they can have impacts on hormone-dependent disease, including breast cancer as well as prostate cancer. So what I was interested in is how we know these bacteria are doing this chemistry, but what is the source? What is the enzyme that's involved? And so we're going to go on a hunt here for what we'll call the benzyl ether reductase. We wanted to find the enzyme that we named benzyl ether reductase that would be responsible for doing this reduction of that benzyl ether bond in the first step of this pathway. And then what we learned from that first step, we applied to the other steps of the pathway to map what was happening here. So first to dive in, we first took pinoresinol, incubated it with Egerthalolenta. These incubations are done in an anaerobic environment in a glove box, although there is water in this glove box. And these bacteria are able to rapidly metabolize pinoresinol to SACO in a matter of 2 to 4 hours. We then took a larger collection of bacterial strains of Elenta and its close relatives. So here is a list of 25 or so strains of Elenta, which means all of these organisms are the same species. Most of their genome is identical, but some of the genes within these organisms are different. And we incubated each of these strains with pinoresinol and found that 2/3 of these strains were able to metabolize the substrate. 1/3 of them could not. And what this difference in metabolism across strains allowed us to do was to perform comparative genomics. And what comparative genomics does is to basically take all of the genomes for the metabolizers and line up all the genomes for the non-metabolizers, and then identify which genes are uniquely present in metabolizers and uniquely absent in non-metabolizers. And those are potential candidate genes for this chemistry. So doing this, we found only 2 genes out of the thousands of genes that are present in an Elenta genome. There were only 2 genes that were only present in metabolizers and not in non-metabolizers. One of these genes was a transcriptional regulator, so not involved in chemistry. The other one had homology to enzyme-like proteins. And so we took that gene, cloned it into E. coli to ask if we put this gene into an organism that is not able to metabolize pinoresinol, does it give that organism the ability to metabolize this compound? And what we found is yes. When we put what we'll call this bare gene into E. coli, this organism was now able to convert pinoresinol into SACO, indicating that this gene was sufficient for metabolism. So collecting all of those genomes from a panel of gut bacteria is a rather labor-intensive process. We wondered if there was a more direct route to get at the same information that we could use to better understand the other steps of this 4-component pathway as well. And what we turned to was RNA sequencing. So in RNA sequencing, we are sequencing all of the mRNA transcripts that are produced when in an organism. So when DNA is transcribed to RNA, then translated to protein, we can sequence those mRNA transcripts to see what genes are turning on in the presence of various stimuli. So we took Elenta, incubated it with pinoresinol, and then sequenced all of the mRNA that was present as a consequence of pinoresinol. You're seeing the results of that sequencing here. So in this plot is represented all of the mRNA in Elenta, and on the y-axis is fold change in how much RNA is there in the presence of pinoresinol relative to the absence. And we were quite delighted to see this transcript here that is very distinct from the rest of the transcripts in this population, was upregulated several thousand fold over the bacteria in the absence of the compound. And it turns out that this transcript was for Bayer. So we have this strategy that we can use to identify genes that are linked to chemistry by being uniquely upregulated in the presence of their substrate. This kind of transcriptional profiling was performed to investigate the other steps in this pathway, the demethylation, dehydroxylation, and oxidative cyclization. And in each of these cases, we found genes that were upregulated that had unique signatures of enzymes that could be homologs for the chemistry of interest. And we have functionally confirmed the activity of EDL for this last step, and the other 2 organisms, we're currently in the process of confirming their activity, although based on their homology to known enzymes with known function, they seem like they are excellent candidates for being able to demethylate and dehydroxylate these substrates respectively. What we then went on to do was to take each one of these genes that is linked to the chemistry in this pathway and ask how abundant are these genes across people. So we took fecal samples from healthy free-living individuals and through qPCR measured the presence of each one of these genes across that population of people. And what we find is that about 2/3 of people are able to or at least have the entire pathway in terms of the genes that are linked to conversion of pinoresinol to enterolactone. Another 1/3 or so of people do not have that complete set of genes, but most people do. This is interesting to us because not all people are able to equally convert pinoresinol to enterolactone given the same amount of enterolactone, suggesting that there is an important component in this pathway of how efficient this pathway is. So what we think is important is how close these organisms are is key for their catalytic efficiency. And this is an idea that we are thinking about in the lab and that many of the people in the field are thinking about is how can we sculpt the chemistry of the microbiome in order to actually get the chemistry to occur that we want to occur when we want it to occur. How can we control some of these processes? One of the keys to this is thinking about what is the scope of molecules that can be metabolized by gut bacteria. A technician in my lab, Paola Bernardino, took a panel of plant-derived catechol and worked in collaboration with Vayu Rekdal from the Bolska's lab, incubating each of these catechol with that panel of Elenta strains that we saw a few slides back to identify what is the scope of dehydroxylation of these substrates at the 4 position of these catechol that can be metabolized. And what we find is that Many of these substrates can be metabolized. In the darker the color, the more metabolism has occurred. And we see that many of these substrates are metabolized by many of the bacteria in the population. There are also numerous host-derived catechol, like dopamine, for instance, that also get metabolized by many of the bacteria in this collection. Although there are also substrates like epinephrine that are not very abundant in the gut that don't tend to get metabolized by these organisms. When we look at drugs and siderophores that also contain catechol motifs, there's much less metabolism of these compounds. And this suggests to us that the bacteria are evolving to metabolize most efficiently and effectively the substrates that are most abundant in the context of the gut, which are some of these host-derived catechols and plant-derived catechols. Current areas of gut microbiome research in my lab are to examine the role of gut bacteria in the gut-brain axis, which is how gut bacteria impact functions of the brain. We're also examining molecular level mechanisms by which gut bacteria interact with dietary fiber and metabolize and inactivate drugs. Just for a brief teaser of something to come from the lab, come out of the lab in the next month or so. We're investigating the role of the gut microbiome in Parkinson's disease. Parkinson's disease is a disease that is characterized by motor dysfunction that occurs when neurons in the motor cortex of the brain die. And what we have been examining is why and how. What are the processes in the gut that are leading to this? There's several pieces of evidence that suggest that Parkinson's is actually originating in the gut, not in the brain. So a phenomenal postdoc in the lab, Dr. Ortiz, has been examining this process, and the details will be forthcoming, but what I wanted to share here is that we've been taking germ-free C. elegans that are models of Parkinson's disease and colonizing them with bacteria in different ways and seeing some really fascinating phenotypes. So here you're seeing a video, hopefully this is coming through okay, of a worm that is moving quickly. This is a worm happy with life, moving with typical motor function. This worm is barely moving. This is Parkinsonian-like motor dysfunction. And the only difference between these worms is what is in their gut microbiome. And we're characterizing what are the specific molecular signatures of microbiomes that are responsible for these really dramatic differences in phenotype that we think are important for understanding Parkinson's. So stay tuned for more details there. Here's a throwback picture from the Sigmund lab, and Turnbaugh lab is where the pinoresinol work was performed. And here is a shout out to the folks in my lab who are making it so much fun to be in this job and to answer some exciting questions, I think, at the intersection of chemistry and the microbiome. And if you're ever in the Southern California area and you want to donate to science, we're always looking for donation of stool samples to be involved in research. So if you ever want to stop by and be involved in the science, we'd be happy to have you.
Well, that's a very interesting final comment. Yeah, lovely talk, Elizabeth. Really great. And again, there's questions coming in, and just for the sake of timing, I would suggest let's answer the questions in the chat and keep the discussion going there. So once again, let's join me and thank Elizabeth for a really interesting talk. You know, definitely moving into new areas beyond where she started, and also making it very accessible for us to follow. So thank you very much. It's great. Okay, so our last speaker is Kerry Engel, and Kerry also had a huge impact on the CCHF, even though he was only a part-timer, because he was involved in the center for about a year, and then went to study at Oxford with Professor Veronique Gouvernet, and also, I believe, spent some time at the University of Tokyo as well, so in collaborative projects. But even so, his impact on CH functionalization was huge. Beyond the research publications he had, he's actually a co-author on 3 immensely important reviews in CH functionalization that are now being cited over 6,000 times together. So really very, very impactful and very scholarly work that he did there. After that, he went to do a postdoc with Bob Grubbs, then came back to Scripps in 2015 as an assistant professor, had an immediate impact where his research had a huge impact. And in 2020, he was actually promoted to a full professor. So a very fast development of his program. So we're very much looking forward to the talk. The title is Oxidative Alkyl Functionalization via C-Alkynyl CH activation. So looking forward to the talk.
Well, thanks so much, Hugh. Let me go ahead and get this loaded. Thanks everyone who's hung on throughout the session here. Is this clear, Rio or Hugh?
It's not sharing yet, Gary.
Okay. Well, that would not be a good time to start then.
So while we're waiting,
Okay.
Again, want to thank the audience to be involved. We've had up to about 380 people join today, so it's really been great to have so many people participating and attending at this meeting. All yours, Giri.
How are we looking now, Hugh?
Looks great.
You'd really think I have this figured out by now. Well, it's great. It's great to be here, and thanks to Hugh and Rio for organizing this and for the invitation to be here and to close out what's been just an awesome action-packed filled symposium. And so, reflecting back on my time in the CCHF, I was there, as you said, in the very early days. I attended the first ever CCHF symposium back in Emory, and I remember leaving that event just feeling like I was part of the Manhattan Project for organic synthesis, being asked to work together with some of the brightest minds across the country to tackle huge problems in reactivity and selectivity control. And I left feeling very optimistic and positive about the power of collaborative work and this interplay between mechanism and catalyst discovery that hopefully you'll see pervade my talk. Certainly something that I've tried to take forward in my independent career. Of course, I also had the opportunity to work on some really exciting projects through the center. And so shown here is a photo of me working alongside Hengbin Wang, then a PhD student with Hugh, who visited us for a couple months in 2011 in San Diego to work on this project where we applied successive or sequential CH functionalization to rapidly generate structurally complex targets, specifically these analogs of a natural product lithoformic acid bearing oxygenation patterns that differ from the natural product. And one of the pieces of sage wisdom or advice that I got from Jin Kwan during this time was make sure in any collaborative project, you always get a photo of yourself and your collaborator doing some work together, because you have no way of knowing in advance whether it's going to be successful or not. And then at least you have something to show the funding agency if it completely goes haywire. But that wasn't the case here. We actually got a nice publication out of this this project, and this served as really important data when I then went and gave academic job interviews. These are slides actually taken directly from that slide deck, showing not only the synthesis of lithoformic acid itself using this ligand accelerated CH olefinational reaction that I had helped develop during my PhD, and then alongside is this sequential CH functionalization approach to analogs that Hengbin really spearheaded, and I was there to be a cheerleader and help provide some advice on the challenging CH alkylation step. And you see, I think one of the cool things about this, reflecting the philosophy of the center, is the use of multiple mechanistically distinct CH functionalization approaches that really come together in a beautiful synergy. And I'm happy to say I've continued to maintain a friendship, both personal and professional, with Hengbin over the years. Most recently, he hosted me as an invited seminar speaker and consultant at FMC Stein, where he's currently a discovery chemist. And then when I launched my independent career, I had the chance to actually reflect on some of the things that I had learned in CH functionalization. So I had the opportunity to write this invited review for Pure and Applied Chemistry. It's actually my first independent paper. And then a couple of years after having left the center, I was actually invited to write this highlight of a real breakthrough that came out of the center back in 2016 in Nature on really one of these remarkable sort of mission to Mars challenges in selectivity control. And so then moving into my independent career and thinking about a research project that would be meaningful, I thought it would be exciting to use what I had learned in terms of strategies for selectivity control and then apply them to a slightly different problem, namely alkene activation. Specifically, we were hoping to take advantage of the now well-established reactivity of palladium-2 and serving as a pi-Lewis acid activation for mediating the addition of nucleophiles to the CC pi bond, or alternatively in HEC-type migratory insertion, and of course this sort of this reactivity paradigm is well precedented, dating all the way back to the initial discoveries of the Wacker process back in the late 50s and 60s, and then do something a little bit different here is intercept with a third reaction partner in solution, and then hopefully be able to convert alkenes into a diverse collection of modularly functionalized carbogenic skeletons containing vicinal functionality. That was the idea, but no, by no means were we the first to think this would be an exciting approach. I've highlighted here papers from many of the pioneers who came before us in this area. But in reflecting on that work and the work of others, we recognized three problems that we thought we could potentially address in our own research, and those are highlighted here. How to control regioselectivity, particularly in the absence of strong steric or electronic bias in the alkene substrates of interest. How to suppress beta hydride elimination to avoid alkyl metal chain walking that would potentially erode selectivity for the 1,2 difunctionalized product, and then how to understand and control kinetics in a way such that we can get productive three-component coupling without being beholden to the natural proclivity of a nucleophile and electrophile to react with one another in solution. We thought solving these problems would be really critical in unlocking the full synthetic potential of this overall reactivity paradigm. And to fast forward now through quite a bit of research to really get to the point of today's talk, we developed this strategy that addresses these problems, at least in a certain context, which is we take unactivated alkenyl carboxylic acids. The alkene here we call unactivated because it's not strained, it's not in conjugation with any electron withdrawing groups. We attach to the carboxylic acid part a directing auxiliary group, which can be bidentate, tridentate, or monodentate even. And I've shown, and this is exemplified by the venerable 8-aminoquinoline auxiliary group developed in the area of CH activation by the group of Olaf Stagoulis at the University of Houston. So we're repurposing that. This turns out to be the one that works, I think, most broadly across different reaction types and across different metals. And the auxiliary here serves a number of purposes. It allows us to control the regioselectivity of this initial alkene addition event. It rigidifies the resulting alkyl metal intermediate in the form of a metallobicycle, making it resistant to beta hydride elimination. And it can stabilize high oxidation state or high valence intermediates that are formed downstream upon reaction with an oxidant in solution, say. And over the years, it's turned out this overall approach is highly versatile in terms of the metals it can tolerate, the redox couples it can tolerate, and perhaps most importantly, in synthetic terms, the vast number of coupling partners that can be employed and mixed and matched in the system. And here's just a quick overview representative transformations and product types that have been prepared both in our labs, and we've been pleased to see that other groups around the world have not only adopted this general approach, but actually use this exact family of substrates to develop a number of really compelling transformations, at least from my perspective. But what I want to talk about today is actually what we've learned outside of the scope of what we had originally planned, and that has to do with the fact that in solution, when you add palladium 2 catalyst to an alkene, you don't just get clean nucleopalidation. You get a much more complex constellation of events taking place, some of which are well documented and some of which are less well documented. And these include positional migration of the alkene, easy isomerization, a process that is quite widely observed, but frankly poorly understood in many cases. And we've actually recently dug into this in collaboration with CCHF member and Scripps department chair Donna Blackman to elucidate some of the details of this process. And then there are a couple of flavors of CH functionalization, CH activation that can happen from this sort of intermediate. You can lose a allylic proton to form a palladium pial, which can then go on to be functionalized. And this mode of reactivity has been developed extensively notably by Christina White's group. And then there's this bizarre and seemingly sort of counterintuitive event that can take place where you actually cleave the stronger alkenyl CH bond. And though this looks a little bit counterintuitive, this is actually what I'm going to talk about today. And this goes back to a question that we were asking ourselves really from the very beginning of our work in this area, which is these strongly coordinating directing auxiliary groups, which were, as I said, developed in CH activation, are known to promote CH activation. To what extent would that happen with an alkene containing substrate? And if it did happen, what would the selectivity patterns be? There are many CH bonds that could potentially be activated, which would activate and under what circumstances? And then I'll layer on top of that, could that actually be preparatively useful to any extent? And you know, for the better part of our first 2 years or so working in this, the answer was we don't seem to observe it. So it's just not something that seems to be happening for whatever reason, presumably because nucleometallation or microtransferation is just fast relative to this process. But of course, we kept coming back to the fact that in the alkyl, with an unbiased alkyl chain, these strongly coordinating directing groups anchor the metal, and then they do promote CH activation and typically form these 5-numbered metallocycle intermediates. So could that ever happen in our system? And the breakthrough on this project area, or the answer to this question is maybe another way to frame it is from this very talented graduate student, Mingyu Liu, who recently defended his PhD and is now a postdoc with Tim Swagger. And Mingyu ran the following experiment. He was trying to, as you can see here, do this anti-Markovnikov hydrooxygenation or the formal hydration, where we add acetic acid across an alkene. We've developed a similar process, hydroamination, so could be extended to oxygen-based nucleophiles. And what he observed instead was this bizarre homodimerized product that contains an alkene-alkene linkage. And if you really look into the details, you'll see that this was formed in only 4% yield, and we're only running the reaction on 0.1 millimole scale, and yet he was able to isolate it, get full characterization, proton, carbon, HMQC, mass, and elucidate the structure with a high level of confidence. So that just shows you what a talented, truly phenomenal student he is. And then this really got us thinking. You know, there are various mechanisms you could draw about how you would make this, but the most logical ones, Occam's razor, Occam's razors here, would involve some kind of alkenyl CH activation event. So we really need to think more about this. And we started to get excited because if you're able to really selectively activate an alkenyl CH bond and then functionalize the resulting alkenyl metal intermediate, then you get access, then you're able to take it relatively readily accessible alkene starting materials. I'm thinking here mono-substituted or di-substituted, and convert them into more valuable, more difficult to access functionalized alkene products. And here we thought the types of products we could access would nicely complement those that are accessible via Walker or Mizuroki-Heck type chemistry, both in terms of stereochemical outcome and in terms of the coupling partners that could be employed. And so then our guiding hypothesis in trying to push this forward was in thinking about how do we take this process that we've started to come to understand reasonably well, but where we can carry out alkene difunctionalization via pyruvate acid activation, and instead derail it to promote when we want alkenyl CH activation, and then couple. Here we used a second alkene as the model coupling partner to probe this question, and this would be a nice way to access 1,3-dienes through oxidative CH-CH coupling of two different alkenes. That was the idea. And we ran some early control experiments just to orient ourselves, and we found out that aryl CH bonds and alkenyl CH bonds are very different. So there's a system that reported from Deb Mady's group for aryl CH olefination, and that really did not translate at all to the alkenyl system. And we'll talk about mechanistically why that is briefly. So I'll fast forward now through some optimization and show what Mingyu ultimately found were sort of the important components of this, one of which was the addition of an equivalent of phthalate acid as a CMD promoter, concerted metallation deprotonation promoter. That mechanism of CH activation at palladium-2 hinges critically on the presence of a carboxylate base, and phthalate acid turns out to be optimal. If we take a look at other carboxylic acids, they do work, but they're less effective. And then palladium acetate as compared to other palladium-2 precursors is the winner here, presumably because you need to maintain a high concentration of the palladium carboxylate salt in solution, and having halide anions is not beneficial to that. And then another key finding was this oxidant. Mingyu actually identified two reoxidation systems that work well. You can either use stoichiometric manganese oxide or co-catalytic cobalt acetate in the presence of O2 environment, depending on whether you have access to an O2 cylinder or not, or want to deal with the added safety risks of running reactions under O2. So either works. And then Mingyu teamed up with a really talented visiting undergraduate student, Pusu Yang, who at that time was at Nankai University, now has moved on to SIOC, where he works with Shuli Yu. And together they looked at the substrate scope. There are many examples that they covered. I'll just highlight a few of the key points. So in terms of styrenyl substrates, the styrene can be substituted with electron-rich, electron-poor groups. Some heteroaryl groups are tolerated here. But importantly, and I think this is one of the points that's different compared to literature precedents, styrenyl substrates are not the only substrates that work. Actually, these challenging 1,2-dialkyl substituted alkenes work well. They're super site selective. There is this competitive EZ isomerization process that's happening in the background, and that erodes the EZ selectivity a little bit. So if we go in with Z stereochemically pure starting material, we get some erosion, but still get reasonable selectivity out in the end. And in addition to alkenyl carboxylic acid derived substrates, we can also flip the connectivity here. Here's an example where we do alkenyl amine substrates using a structurally related picolinamide directing group. And then we can also do alkenyl alcohol derived substrates by linking the aminoquinoline group through a carbamate connection, which can then readily be cleaved. So I think one of the themes and long-term goals of the center has always been trying to understand the origins of site selectivity, and this is something we were curious about as well in this system, particularly why the catalyst seemed to prefer to go after the relatively strong alkenyl CH bond as opposed to the weaker allylic CH bond. And so Malkampi Karunananda, a postdoc in the lab, under the collaborative mentorship of Peng Lu, who we heard from earlier today. This is very much sort of like a CCHF inspired mentorship model, where it's not just who your boss is, who you listen to, who your boss on paper is. It's the one who actually has the expertise that can help you is the one you should go to for mentorship. So Malkampi in her computational pursuits has worked closely with Peng, and in this case, Peng's former student Yan Yan. long. And so we looked at all the different pathways in terms of site selectivity here that could be going on. I think one of the beautiful things of computational investigations is that it not only allows you to understand what happened in the flask, but why other things didn't happen. And so we're able to interrogate that. And so if we compare the allylic pathway, which is shown in salmon, to the experimentally observed pathway, which is shown in burgundy, indeed, the allylic pathway is actually thermodynamically preferred, but it has a much higher a barrier. And then the other pathway, the other alkenyl CH bond activation pathway is higher because it forms a larger metallocycle, and there's a lot of ring strain involved in this. So that one we can rule out. But this is pretty interesting, the difference between allylic and alkenyl. And I think the most intuitive way to understand this difference is that the initial coordination of the alkene from the substrate to the catalyst is quite thermodynamically preferred. It's quite exergonic. And so in the allylic pathway, you need to lose that alkene coordination that is built into the transition state energy. Whereas in the alkenyl CH activation pathway, you can maintain that coordination. Essentially, all it's doing is just slipping to allow the carboxylate base to engage in the CMD process. And so we've also been looking at the mechanism here through experimental techniques. We've made a series of model complexes. Here's a case where we can take an E-configured substrate that reacts more slowly under the reaction conditions and get out a crystal structure of the pi alkene complex that would be the precursor to CH activation. We've actually been able to make the CH activated putative intermediate, although it's actually probably not an intermediate, because what happened with the complex we got out was this bizarre looking dimeric structure where presumably after alkenyl CH activation, two molecules of this intermediate find each other, and what we get out is as I said, kind of a bizarre structure that can be viewed a couple different ways, either as a diene that's bound to two palladium-1 centers, or as essentially a double pi al bound to two palladium-2 centers. And we've been trying to understand how this is formed too. Very likely it's off cycle, and so not directly relevant to catalysis, but it could be a catalyst deactivation pathway. And so we've been looking into it. And one of the things that's emerging, this is unpublished data, but one of the things that's emerging is there seems to be a very low barrier pathway for what seems to be a quite unique CC reductive elimination process that's promoted from bimetallic palladium-2 to bimetallic palladium-1. And this is work that's being led by Malkanthi. So stay tuned for more details about this story as it emerges. And on the synthetic side, one of the things I've always appreciated about intersphere CH activation is that once you make your organometal intermediate, it can potentially be transformed into a range of different organic products, and that's the case here. Our work is part of really a larger narrative where alkenyl palladium intermediates can react with various coupling partners, including those that are not compatible in the classical Walker-Heck type manifold. So Eric Carrera's group has developed some nice alkenyl CH halogenation and alkynylation, and then the Shao and He groups have developed these highly selective and non-migratory CH oxygenation, and Perea and Babu have recently reported this Z-selective alkenyl CH aerylation that complements what you get from a classical heck process. So I think this is a tool that's emerging. Still, obviously, a lot of work to do, but one that my group's been excited to be a small part of. And again, this comes back to this slide I showed before, where we're beginning to understand and appreciate how these different processes are related, and how to encourage the catalyst to distinguish between different pathways when desired. And I'm blessed to be the spokesperson for a wonderful team. All of the credit for this work really and our program in general should be given to them. and of course, I'm appreciative of our sponsors as well. And as I said, really grateful for this opportunity to close out the symposium, and happy to answer questions either in the chat window or offline if you want to email me.
Okay, Kerry, what a wonderful talk, and it's amazing the range you've achieved, and a very, very generous introduction to the CCHF too. That was very, very nice the way you interplayed things. That was wonderful. At this stage, if there's, I think there is a question in the chat, and maybe you could respond to that. But at this stage, I'd like to thank all the speakers. I'm actually personally so proud of all 5 of you and what you've achieved when you were in the center, and it's great to see how you've all developed so fantastically in your independent career. A lot of great novelty and ingenuity in what you're doing, and it's really lovely to see all the different range of science that you've got into. So from me, and I'm sure from the whole audience, congratulations on your great accomplishments, and we're definitely looking forward to the continued development in the future as well. So at this stage, I'd like to bring this meeting to a close. Want to remind you that there's part 2 to come up in about a month's time, and hopefully you'll be able to join us. I do need to acknowledge Rio Ferdinand, who's done all the hard work in the technical aspects to make this meeting run so smoothly. Greatly appreciate your role as managing director of the center. It's been really important for what we're doing, and you're doing a fantastic job there too. So once again, thank you everyone, and this has been a great meeting. We really enjoyed it. Thank you. Bye now, everyone.
All right.
Are we closed off?
On YouTube, yes, but I sent out an email for things now. So if we need to move to the other room, you can go there anytime.
Are we alive now still, Rio?
Yeah, there's not really any way to actually kick off attendees.
Right. No, that's fine. So I want to tell you, everyone, that my comments were exactly how I felt about your talks. You did a fantastic job. So it really was wonderful.
Thank you so much, Hugh.
Yeah, thank you, Hugh.
Thanks.
All right.
You,
So
you know, this is the first time I've talked about CH activation since my thesis defense. So I really had to brush off the old, dust off the old.
Well, you did a good job, nonetheless.
The old notes, I guess, for that. No, it's great. It's sometimes it's fun to have the chance to give a talk of this length, where it doesn't have to be so comprehensive. You can just pick something you don't normally talk about.
Right.
I'll be on the spatial chat now, so I will see you all there, right?
Okay, so yeah, we need to close off, and you're going to close the meeting with the link now.
Yes.
And see you at spatial chat in a few minutes.
Okay, bye.
Bye.